first thing I'd like to do is provide a little bit of a review of what we talked about on Wednesday's class, because I felt that maybe some of you didn't quite capture everything that I was trying to teach. So before we move on to a new topic, I'd like to just lecture for a little while on what we talked about on Wednesday, which was the concept of work and then ultimately a concept of kinetic energy and how these two things are related to one another, um, but are fundamentally different from one another as well. So to begin with, this is chapter 14 material, kinetics of a particle, work, and energy. Um, I think it's helpful if I write down specifically what work means. So work has a very specific definition. Okay? Work is defined in a very specific way. It's the product of displacement and the component of force along the direction of displacement. So it's the product of displacement and the component of force in direction of displacement. Sometimes you'll see people say that work is force times distance, and that's true. In a very general way, work is force times distance. You need both a force and a distance component to determine work. But not all forces do work. Some forces do positive work, and some forces do negative work. So it's not just enough for us to remember that work is force times distance. We also need to pay attention to the orientation of the force, because you see here that we have this component of the force in the direction of the displacement. So I drew this for you in class. Imagine that you have this particle that's on this path, S, and the particle at one point is right here, and then at a later time it moves up the path a little bit over there. Okay? Now we can always locate that particle with respect to some location we call the origin, and we would say, okay, well, there's the initial position vector for that particle, and then at a later time the particle finds itself over here. And perhaps the reason why the particle moves from one place to the next is because there's a force working on it. Maybe it's falling, which would be gravity. Maybe there's a spring pulling it. Maybe it's attached to a rope and someone's pulling that rope or pushing the particle from one place to the next. But if I draw that force that's moving the particle like this in blue, then you can see, okay, well, that force doesn't need to be completely along the path that the particle is moving on. It only needs to have a component in that direction. And so that force F might have an angle theta between it and the path that the particle is moving on. Okay? So yes, work is the product of force times distance, but it's only the component of the force along the direction that this object is moving that we're interested in. So as this particle moves around at a very small amount, the amount of work that's done is equal to F ds cosine theta. Well, we realize that F cosine theta would really only be just that component of the force along the path that we're interested in, right? If we take F cosine theta, that would be this guy right here. Goes back to our original definition of work, product of the displacement and the component of the force in the direction of the displacement. So I don't care about the perpendicular component, which would be F sine theta. I don't care about that because that's perpendicular to the direction that that particle is moving in. Work is defined as the product of displacement and the component of the force in the direction of the displacement. So when I see F cosine theta here, and then I multiply that times ds, I have F cosine theta, and I multiply that times ds, then I am guaranteed to determine the amount of work done over that small amount. Anytime you see that lowercase d, remember, it just means a small amount. Okay? From statics and strength of materials, we understand that we can use the dot product to indicate the exact same thing. F dotted with dr is the exact same thing as the expression above. So these are identical statements. Those are identical statements. Okay? So this allows us to determine a small amount of work that's done over a very tiny distance. But of course, we're generally interested in finding out the amount of work that's done over longer distances. So what do we do in that case? Well, I realize that on both the left-hand side and the right-hand side of this equation, I have differential elements or differential units. A differential amount of work, I have a differential distance. Differential work, differential distance. If I integrate those equations, then that will give me a total amount of work over a total distance, over a larger distance. So that's really all I have to do. So the work that's done from position 1 to position 2, this is notation that we use. Work, we use capital U to indicate work. That's done from location 1 to location 2, or position 1 to position 2, is simply the integral of the right-hand side of that equation. So from R1 to R2 of F dot dr, or if we do it in scalar notation, S1 to S2, F cosine theta ds. And see, here all I've done is I've brought that cosine, which was originally put that at the end of my expression. I could always just move this in between the f and the ds. That's all I did there. Okay? So if I want to know the total amount of work that's done from position 1 to position 2, which we have to define, then I would just integrate f dot dr or f cosine theta ds. Piece of cake. Now, there are many instances in which theta is constant and f is constant. So I'm going to say if f and theta are constant, then we can do a pretty cool thing. We can take f cosine theta and bring it out of our integral. So if f and theta are both constant, then the work done from position 1 to position 2 is equal to f cosine theta, and we're left with from S1, S2, ds. Now that's a pretty simple integral for us to evaluate. The work done from 1 to 2 is f cosine theta, S2 minus S1. This is only true if both f and that angle that the force makes with the displacement are constant. If that's true, then we can immediately jump to this equation that I've boxed. If f changes over time or over position, or if the angle it makes with the displacement changes over time, then we have to use one of these two equations up here that I'm circling. But there are many instances where f and that angle are constant. I use that example where I have my daughter and she's riding in a sled. But imagine that I have this box here, and I'm pulling this box with some force, a constant force. It's resting on the ground, so there must be a normal force supporting it. There must also be a weight force pointing down. There might be friction working against me. So if I'm pulling this object with a constant force and a constant angle, then guess what? I can jump to this equation down here because my force will be constant and that angle is constant. However, if I change the amount of force that I'm using over time, I can't use this equation. Or if I change the angle that I'm pulling this box with over time, I cannot use this equation down here. I would have to integrate with this expression up here. Okay? So work is a force times a distance. That is correct, and people do say that. Work is force times distance. That's okay. but it's a little bit more than that. It's the product of displacement, or distance, and the component of the force in the direction of the displacement. Now, this is really important because if we go back to this picture that I have here, as I'm pulling this object, you can imagine that it's going to move to the right. At a later time, it's going to move itself to the right. Well, look, the weight force is pointing down. The normal force is pointing up. These two forces are both perpendicular to the direction of the displacement. So even though those forces are working on the object, they do no work over this process. They are perpendicular to the direction of movement, so they do no work over this process. Cosine of 90 degrees is 0. So the work done by any force that's perpendicular to or 90 degrees to the direction that it's moving does no work. That's a really important concept. There are two forces, which are called conservative forces, that do work according to a very specific equation. The first conservative force that we learn about is weight. The work done by the weight is always equal to negative W delta Y, change in Y. Negative W times change in Y. You can remember that. That will never change. That will never change. You can put that on your cheat sheet. The other equation that we want to remember is the work done by a spring is equal to negative 1/2 K times the quantity S2 squared minus S1 squared. Now this is important to understand what each of these terms really means. Now in the work done by the weight, this W here is the actual weight of the object. Delta Y is equal to Y2, the final Y position, minus Y1. We have to assume that Y is positive upwards in order for us to use that equation right there. We need to assume that Y is positive upwards. Okay? And that makes sense too. If we go back to our drawing here of the crate, I'm pulling it to the right. Delta Y is equal to 0 in this case because it's just moving horizontally. It's moving side to side. So if it's only moving horizontally or side to side, then Y2 is equal to Y1. And so there's no work done by the weight, which makes sense as well. We already said that. Now in this work done by a spring, we have this value K. This is known as the spring constant. Spring constant is not a force. Remember that. The spring constant is not a force. It is a constant value that indicates how strong that spring is. Is it really bouncy or is it really stiff? It has units of things like newtons per meter, meaning how many newtons would you need to apply to that spring to elongate it 1 meter? It can also be written in pound force per inch, sometimes pound force per foot. So clearly the spring constant is not a force by itself because units of force would just be newtons or pound force. But the spring constant has units of newtons per meter or pound force per inch or pound force per foot. It's a force unit per length unit. Okay, so don't confuse those. Now that's a value that generally is given to you in a problem. What about S2 and S1? S2, S1, this is the elongation or compression of spring. It's not the length of the spring. We need to remember that. S does not equal the length of the spring. It indicates how much the spring has been compressed or elongated with respect to its equilibrium position. S1 is always equal to the length of the spring at state 1 minus L naught, where L naught is your equilibrium length. Therefore, S2 is going to be equal to L2 minus L naught. Okay? It's the amount that the spring has been stretched out with respect to its equilibrium length. The equilibrium length is just simply the length of the spring when there's no force applied to it, when it's just sitting there. Okay? The spring itself is going to have some length, some natural length to it. Call this L naught. But I can take this spring and I can push it together. Or I can take this spring, and I could call this L1 for instance, or I could take this spring and I could stretch it out. Call this, say, L2 for instance. Maybe it starts off compressed and it ends up stretched out. S1 and S2 is not the length of the spring, remember. It's the distance that it's been compressed or stretched. This would be S1 here, the difference between the equilibrium position and its new length. S2 would be this distance here, the distance from its equilibrium length to its new length. Okay? It's the amount that it's been stretched out or compressed by. It's always with respect to the equilibrium position. Okay? Once you understand that, then you can memorize these equations that are up here in the upper left-hand corner. The work of the weight is equal to negative W times delta Y. Delta Y is just Y2 minus Y1. The work of the spring is equal to negative 1/2 K times the quantity S2 squared minus S1 squared. You can memorize those. Those do not change.